So another question that came from the forum was more about what makes a host a super spreader and a super shedder. And it also came up with the 80-20 rule. So I'm going to throw it all to you. What do we know? What makes a host a super spreader, a super shedder?
Well, we've done something in the lab on super shedders. And going back to the co-infection. So we had rabbits with chronic infection, so the respiratory bacterium, and 2 worms. And we found the rabbits co-infected shed more bacteria than rabbits that didn't have worms. And also in this bunch of co-infected rabbits, there was always a couple of outliers, animals that shed huge amount.
And what exactly do you mean by shedding in this case?
Amount of Bordetella, in this case particles, shed on a surface. So this is shedding by contact, just impregnating a surface with bacteria. But also we did the same, keeping the object just a few centimeters away from the nose. So there was also aerosol shedding.
Right.
So these animals breathe and they shed bacteria. And if you are co-infected, you shed much more.
But amongst those, there were some that shed even more. So there's some super shedders.
Yeah. So co-infections turns you into a big shedder, and some of these co-infected individuals shed disproportionately more than others.
Okay.
So in this instance, your rabbits are genetically similar, I suspect. They might be genetically identical.
Not really. They are sold as outbred, but there is a lot of inbreeding. Let's say.
So in many systems, particularly with white mice, when they do those experiments, they still see it. So despite genetic variation, and incidentally, the medics always tell us it's genetic variation, there's other things going on. Co-infection's one, immunosuppression would be another one, your dietary state could be another one. So there could be multiple factors. And we don't really know how they interact. But we do see it in cattle, don't we? Cattle, super shedders and cattle, in E. coli work. So the cattle's perhaps similar genetically and not, and then they're all on the same diet, but they still do it.
There is something else. You're not just a super spreader. You go in and out of this status all the time. So there is individual variation, but also there is within the same individual variation over time. So you super shed and then stop. You super shed and you stop, or you decrease.
So there is a general rule about this, isn't there? The proportion that are in.
It's not obvious, and it's not really clear why there is this behavior of sort of pulsing super.
So I was coming back to the 2080 rule.
There is much discussion in the literature that the 2080 rule applies here, that 20% of the hosts are responsible for 80% of the transmission. And it is true in something like worms that typically 20% of the hosts have 80% of the worms in the population. So the numbers tend to hold up in some of those contexts. Much like many other aspects of human exploration and endeavour.
So I think one of the problems we have with identifying super spreaders is separating those individuals that are super shedders, i.e. those that are shedding a lot, versus those that have high contact rates. Because if you have measles and you have more contacts than somebody else, then the likelihood of you passing it on to more is increased. But we don't often have the right data to be able to separate those.
And it can feed back on itself, right? Once an individual is starting to become heavily infected, they become more susceptible to more infection. So the worm population, for example, can build up, and then that individual becomes a super shedder because of that initial variation in contact rate.
There's some interesting. I remember years ago there were some interesting studies for malaria of how different people are attracting mosquitoes.
That's right.
There's smelly people.
Smelly people, and the most famous one is pregnant women are very attractive to mosquitoes.
Oh, really?
So, partly because of the increased heat and increased CO2, bigger surface area as well.
But I think it's really important to be able to say that these individuals move into, this is what you said, that it's a dynamic thing. So you'll be a super shedder for a period of time and then not for another period of time. So we studied this in the zoonotic disease, tick-borne encephalitis, and showed that males became super shedders when they were highly sexually active, but when they weren't, then they came back, while the females never became the super spreaders.
But the super shedders and the super spreaders are, if we could find those and predict those, you could get disproportionate bang for control measures. So it's a very important question.
But it seems like that would depend, especially on the super spreaders, on the structure of the network. So if you had a very fragmented system and you ended up having people who were highly connected just within their cluster, then that wouldn't have the same impact of a highly connected system in which you had a few people who were disproportionately connected. There's an interesting interrelationship here, at least Sheldon Cohen studies, where he found people who had fewer social relationships. Actually, when he did clinical trials where he gave people versions of the flu, I think it was an influenza virus, and people who were more socially isolated actually shed more. And his argument, and the arguments he's been playing out, is the stress of being isolated, being lonely, is changing what's going on. But
because that's interesting, because that's kind of the susceptibility effectiveness side of things. There was the interesting computer model a couple of years ago where they said that actually the best strategy you have is that you should pick people at random and then vaccinate their friend. because you're most likely then you're more likely to pick people who are very highly connected in the network. So that's the optimum way to reduce the exposure and circulation.
Vaccination.